Quick introduction here of Jef. Longtime member of the club. He doesn't come to meetings because of schedules and stuff. But Jef has an extra class license, works as a member of the Placer County Radio Services team, supporting all the first responders, mostly via the mountaintop repeaters that he works with, and supporting the SCADA for public utilities, mostly in very low places. Waste water runs and that kind of stuff all runs downhill. So Jef kind of is there to catch it all, so to speak. He enjoys the technical side of ham radio, building antennas and projects with Raspberry Pi, Arduinos, and the like. But his main interest is in emergency preparedness in all its forms, and that's where NVIS comes in. So I turn the mic over to Jef.
Okay, thanks, Greg, and thank you for that very inspiring talk on astronomy. You know, I was going to begin by contrasting and comparing NVIS, which uses very long wavelengths and is for local, with DX, you know, shorter wavelengths and distance. But you really expanded the context, you know, talking about light years of distance and nanometers in wavelengths. So wow. This is a presentation that I put together about a year ago for Placer County Search and Rescue and OES, and so thank you for the opportunity to present it to the club tonight. And again, it's kind of a complement to DXing. It'll be looking at antennas and propagation from a kind of a complementary or opposite point of view. So I hope that everyone finds something of interest in it. The presentation is available in the club files, and I'll try to pause for questions after each of about 3 sections. So we'll talk about what is NVIS, and then I'd like to get into a little more detail on ionospheric propagation, frequency selection, antenna optimization, and then very briefly touch on some associated technologies and any discussion that people might want to have. So what is NVIS? NVIS stands for Near Vertical Incidence Skywave. It's a radio propagation path providing local and regional communications out to a few hundred miles. And it's regardless of terrains, such as mountains and canyons, and it's independent of infrastructure, such as repeaters. The radio waves travel nearly vertically upwards into the ionosphere and are refracted back down within a coverage area extending, like I said, to about 300 or 400 miles. The picture on the screen here shows transmitters and receivers, which would normally be hidden from each other because they're in canyons separated by tall mountains. Radio waves going up, passing through the D layer, which absorbs, and it's about 50 miles up, roughly, going up to the F1 and F2 layer, which are more like a couple hundred miles up, and then back on down. And so it has some very strong properties for emergency communications because it doesn't depend on the repeaters that we're used to. You can set up very quickly and you can talk reliably regardless of terrain. So the advantages, again, solid coverage with no skip zone. We'll talk a little bit more about what a skip zone is, but anyone who's worked with DX knows that they can't hear people who are close to them, but they may hear someone 1,000, 2,000 or more miles away. Requires no third-party infrastructure, such as repeaters or satellites. So that's a very strong reason for its emergency strengths. It's relatively free from fading because of the short path. The antennas can be very simple, easy to set up. Like I said, tall mountains and deep canyons are no problem at all. Direct and short path loss, path for low path loss. And NVIS techniques can dramatically reduce the noise that you typically hear on the lower bands. If you ever listen on 80, 40 meters, you'll hear thunder crashes, lightning crashes, especially in the summer. And with the right NVIS setup, you minimize that kind of noise, which is typically 1,000 or more miles away, and you emphasize signals which are coming from only a few hundred miles away. Low noise, with its noise rejection and low path loss, it'll work very well with low power. The military uses man packs with, say, 30 watts, works very well. You really never need more than 100 watts. The disadvantages, well, both stations should be optimized for NVIS with the proper horizontal antennas. It takes a little greater skill and knowledge to select the appropriate frequencies, and the choice of frequency changes throughout the daily and the annual cycle. Who uses NVIS? And I'm going to kind of breeze through this quickly. Again, the presentation is available in the files. DHS and FEMA, Cal-OES, the military, Red Cross. It's been used for many important incident command structures, and we'll just touch on those briefly as we move forward. Homeland Security has a program called SHARES, Shared Resources High Frequency Radio Program. It's for government agencies. They get together and practice and do exercises. It's all done on the lower HF bands, and there's a URL down here for more information if you're curious. Cal-OES, every Monday at 2000 hours, that's 8 o'clock, local on 80 meters, you can listen to Cal-OES Oxcom do their statewide net. And it works very well throughout the year. Then again on Wednesdays every week, in the morning now, on 40 meters, they also have the net. And so twice a week, you can listen to Cal-OES practicing. And it gives you a really good idea of how well NVIS can work across the entire state of California. The military made a lot of use of NVIS. Now there's a lot more emphasis on satellite communications, but back on D-Day, they were using NVIS to coordinate things. It was used in Vietnam to communicate, to mitigate the effects of heavy foliage, because VHF and UHF don't work well with the heavy foliage, but the longer wavelengths with NVIS provided reliable communications. Mars is a program that used to be very busy with providing telephone service for our service people overseas. It's faded away a bit, but it still exists. Modern military aircraft are still equipped with HF radio. You'll find a long wire antenna below the fuselage. And the military still has equipment for setting up base, mobile, and temporary field comms. Again, kind of secondary to satellite, but if we lost our satellites, this would do the job. Again, independent of infrastructure, independent of terrain, low to medium power, difficult to trace. When you shoot your radio waves straight up and they come down in a surrounding area, it's hard to tell where they came from, because you can't do terrestrial radio direction finding. I crossed out the last line because I just wrote it wrong. The point was supposed to be that in the case of a high altitude EMP attack, we'll talk more about that, it's very quick and easy to set up NVIS, so it's resilience rather than robustness. Areas practices with HF. We have Skywarn, program of the National Weather Service, RACES, Mars, we've talked about that. So more amateur radio and amateur and military affiliate programs. Red Cross, AreasNet. On Saturday mornings, the Bay Area Red Cross has a weekly net to test NVIS on 80, 60, and 40 meters. I attend that sometimes. It's a really good way to get a feeling for how well it works, how well your equipment's working, and the capabilities. In the mornings is California Rescue Communications, based in Southern California mainly. It's not so much NVIS because it's 40 meters and it's too early in the morning, but it does provide a mode of regional communication, one they can hear each other through the Chinese broadcasting. On Fridays and weekdays around noon, there's the California Amateur Radio Service nets, and on Fridays they emphasize emergency power. That's 40 meters, and around noon, 40 meters is usually good for local. And then there's Saturn, the Salvation Army Team Emergency Radio Networks, just another example. And the new net, many people know about the new net. That gives you a really good idea of where you can hear people. But you have to keep in mind that a lot of those antennas are not optimized for NVIS. So the signals don't really punch through the noise as you might expect if they were proper horizontal antennas, but you can really hear a wide, the wide coverage that people are able to achieve on 40 meters around noon every day. A couple more examples: Western Public Service System every night at 6 o'clock p.m. A good social group, as well as Public Service System, and the West Coast SwapNet, and many more. Disaster communications. These are actually examples of examples where FEMA went in and HF was amateur HF was part of their emergency preparedness and emergency response. And you can just see for yourself, 2003, the Northeastern blackout, VHF and HF, Katrina, large earthquakes in Asia. Usually there are national exercises every year, and so on. So it is taken very seriously. A couple years ago, actually 4 years ago now, Cascadia Rising was a large FEMA exercise based on the possibility of a large earthquake and tsunami hitting the northwest coast. And they emphasized the importance of amateur radio as a backup for satellite or as a replacement for satellite. And they found some weaknesses where people didn't have sufficient training, sufficient equipment, sufficient knowledge of amateur radio communications to provide in an emergency such as that. So just another example emphasizing our value for emergency preparedness community service. EMP. This is something that could happen, at least some of us believe so. Government has plans to handle an EMP, electromagnetic pulse attack. And in this case, this is a case where HF radio could fill in if our VHF, UHF infrastructure was destroyed on the ground or disabled temporarily. Satellites could be disabled, but HF can be quickly put up. The antennas are simple, and we can communicate over long distances reliably. Coronal mass ejections is another possibility. Back in 1859, there was the Carrington event. It was a major solar flare. It destroyed the US and European telegraph networks. It started fires. It shocked the telegraph operators. And back then, they didn't really know what it was, but it was a solar flare that hit the Earth with enough intensity to create high voltage on the power lines and the telegraph lines. In 2012, there was another one, similar magnitude, but it missed us by 9 days. It's been calculated that the chance of Earth being hit by another Carrington-class storm within a 10-year period is about 12%. Something to think about. Just an impressive picture of the sun and a solar flare. And I'm going to see if I can open up for any questions at this point before we move into ionospheric propagation. Are we available to take questions?
Yes, go ahead. If anybody has any questions, go ahead and give them at this time.
Okay, moving ahead. Let's talk a little bit about ionospheric propagation from the point of view of NVIS. It's going to be a little different than the ionospheric propagation when we're considering DX. Again, NVIS is a coverage area of a few hundred miles radius. We try to send our energy, our radio energy, nearly vertically up into the ionosphere through the D layer, which absorbs, up to the F layer, which refracts, and it comes down. It's almost like shooting water from a hose straight up into an umbrella and having it scatter and come down in a kind of a circle all around you. Here's a kind of a picture showing with the center in Auburn, the kind of range that you could reliably expect all the way up past the state of California line. And this is conservative. It can easily go further, but this is maybe true NVIS. Well out into Nevada and in the south all the way down to the bottom of California. Again, a picture of the propagation showing the independence from terrain features. So here we have just a little bit of a zoom in on the ionosphere. The key features to note are you have day and night differences with the ionosphere. In the daytime, you have the D layer, which absorbs. It's about 25 to 55 miles up, and at lower energies, such as at the 80-meter wavelength, it absorbs a great deal of the radio strength. And so you have to get through that to have any chance of getting to the F layer and refracting back down. As after the sun goes down for the night, then the D layer fades away almost immediately, and 80 meters comes alive. But during the day, 80 meters is not really a good choice except for very local, because of the absorption in the D layer. What we really care about is the F1 and F2 layers. And in the day, as the radiation from the sun charges up the ionosphere, the F1 and F2 layers separate and do a very good job of refracting energy. Depending on the wavelength that you're sending out, it'll refract that energy back down to the Earth at some distance. And we'll look at that in just a moment. So here we have the F1 layer and the F2 layer, showing that from the transmitter at 40 meters, we start to refract and come down at some distance. At 20 meters, which is a shorter wavelength, which penetrates further into the F layer, comes down at a further distance. 10 meters, it penetrates even further and higher, comes down much further away. That's why with the higher frequency, shorter wavelength HF bands, you can expect greater distance, but you don't get the kind of local reliability that you would with the lower frequencies. And what it doesn't show here is 80 meters and 40 meters, but of course they would be even lower, smaller penetration into the F layer and more local coverage. If you get too high in energy, like in 2 meters, which shows here at the top, 2 meters just penetrates and heads out into outer space and heads off to the Andromeda galaxy. Here's another view of the ionosphere, and what it's showing us here is skip zones, where if you're using for say 20 meters, you won't hear things more than a short distance away. You skip right over it, as everyone who's worked DX knows. So skip zones can be a problem. The nice thing about NVIS is you don't have any skip zone. You have solid coverage within a few 100-mile radius. Also, what it's showing us here is the ground waves, which can be a problem. Ground waves go out maybe 40 miles at 40 meters, more like 60 miles at 80 meters, more like 80 miles with 160 meters. Ground waves are the reason why you hear radio stations like KGO, for example, in the Bay Area, traveling great distances at night. It's a ground wave propagation. So again, 40 meters at about 40 miles out. And what we notice sometimes when we're trying to operate NVIS is that we'll be getting a combination of ground wave and also getting the skywave from the ionosphere at the same time, but out of phase, and it'll cause distortion. And that's one of the problems you can have if you're radiating from a vertical antenna, which is good for ground wave rather than horizontal antennas on both ends. So ionospheric variation happens daily. In the late morning through the late afternoon, the F1 and F2 layers are separated. The D layer is fully formed. And so you have to select a frequency that's high enough to penetrate the D layer, but not so high that it penetrates the F layer and goes into outer space. So generally in the afternoons, 40 meters, around 7 megahertz, is a good choice. Early mornings and after sundown, the F1 and F2 layers combine to form a weak F layer. The D layer disappears, and so you have to select a frequency low enough to be refracted by the F layer, and generally 75 meters is a good choice. Otherwise, mid-morning, near sunset, in between, 60 meters, 5 megahertz is a very good choice. And that's some real prime real estate, which is why we have it on a secondary basis. The military has it primary because if they need to do NVIS, they are primary on the 60-meter band. Oh, also it bears saying that right now with the sunspot cycle being the way it is and weak ionospheric charge, 60 meters is the best bet pretty much all through the day. This is the same diagram as before for review, don't need that. So here we have a very useful tool for seeing the state of the ionosphere in terms of NVIS propagation throughout the day. It's the San Francisco Ionosonde. They're shooting radio waves straight up and recording the time delay between the time they're emitted and the time they return from being reflected from the F layer. And they're able to create these maps. And what you can see here is this first map was taken at 5:15 a.m. while the sun is still down. This was in February of last year. And you can see this red here shows that the ionosphere is not very charged. Even 80 meters, which would be 4 megahertz, even that has gone long. And really, if you want to have reliable communications locally, you might want to use 160 meters. 80 meters will still work, but not as efficiently as you might want. Then we move ahead in time an hour later, and you can see that the red spot has shrunk, the yellow is starting to take over, and 80 meters is now really becoming the choice for regional communications. The D layer is still not a problem because the sun just barely came up, and so 80 meters does a good job. An hour, well, a little less than an hour, 7 o'clock, the red spot is getting much smaller. 80 meters is now strong. 7:17, 80 meters is the place to be. And at that point, if you look at the chart up here, it's yellow, but you don't know if that's 4 megahertz, 5 megahertz. It's something less than 6 megahertz. So 80 meters and 60 meters are both really good with these conditions, providing solid coverage within this entire yellow circle. Later in the morning, it's time to start looking at 60 meters or possibly 40 meters. And later in the afternoon, 3 o'clock p.m., it's coming back. And this is February of last year, so sun's going down, and we're back to conditions which were almost the same as they were at sunrise. Okay, we're just about covered everything on the ionosphere. Just want to emphasize that in the winter, we have shorter and weaker ionization of the F layers, but we also have weaker absorption by the D layer. In the summer, we have longer and stronger ionization of the F layers, stronger absorption by the D layer, and much stronger noise due to worldwide lightning storms. What this all means is that the choice of frequency, the choice of band during the day will depend on these conditions. Sunspot cycles. People involved in NVIS as well as DXers will know that we are at the very bottom, nearly at the bottom, just starting to come out of the last cycle. So just about as bad as it could be for DX and NVIS both. But 60 meters, 80 meters, they're still good during the day. This is a zoomed in version showing the same thing. Just about as bad as it could be. We have another 5 years or so before things will be hopping again. Which doesn't mean DX doesn't exist, as you know. Okay, I'll open it up for any questions at this time. I hope we're not going too fast.
Yes, can you hear me? AI6US?
I hear you, Brian. Do you hear me?
Yes, I do. I was kind of curious. The mapping that you had done, the prediction or the forecasting. What was the website for that, or do you have that in the reference? I missed it.
Yeah, I'm trying to think what would be the best way to give that to you. If you just do a Google search on SF or San Francisco Ionosonde, that will certainly find it for you.
Okay, I copied that down. Thank you very much.
Okay. So we've talked about who uses NVIS, kind of what its strengths and weaknesses are, and we talked a bit about how important the ionospheric conditions are for choosing the right frequency. Any other questions before we move on to antennas? Okay. So a good NVIS antenna will radiate with predominantly horizontal polarization and substantial vertical directivity. We want that energy to go as much as possible up, straight up into the ionosphere. We want it to spread out maybe as much as about 45 degrees. And that's what's going to provide us with the reliable regional communication out to a few hundred miles. This is quite opposite from a DX antenna, and we'll look at some patterns now just to see the difference. This antenna pattern, takeoff angle pattern, is showing us an antenna that will not work for NVIS. This is just your standard 15-foot whip. Actually, any vertical whip antenna will have a radiation pattern like this, and you can see it's mostly off the side lobes, off to the sides, and very little radiation straight up. And so that's why when, for example, during the noon net, people are checking in during the noontime with whatever antenna they have. A lot of them have vertical antennas, and doesn't do a really good job for those kinds of short distances because their radiation is going out sideways rather than up. This is showing for a horizontal dipole at various heights how the height has a huge difference on the pattern, and we'll cover this in a few slides. But here you have in the kind of a magenta color, only a very low antenna, 0.02 wavelengths low, and you can see the pattern is kind of this round shape. It's not really stretched out, but it's also being strongly absorbed by the Earth. If we go up to 0.06 lambda, 6/100ths of a wavelength, it's still very low, but now it's much stronger, but still greatly absorbed by the Earth. Once we get up to about 0.2 wavelengths, roughly a quarter of a wavelength, it's ideal for NVIS. The energy is going as well as possible upward, not wasting energy going sideways. And if we look at the red pattern here, which is showing 0.4 wavelengths, almost a half wavelength, you can see it now the pattern is moving into a stretched out to the horizontal lobes, getting more like a DX antenna and not as much like an NVIS antenna. We'll see that again in the next slide. So this one really makes it clear, I think. If we start down at the bottom, we have a low antenna. Moving to E here, we have a tenth of a wavelength above the ground. It's a little stronger. Moving up to quarter wavelength. This is ideal for NVIS, roughly, where we have maximum gain, minimum absorption in the Earth, and we're putting a lot of energy into these upper angles. Excellent for NVIS. But if we get that antenna, too high, if we go from a quarter of a wavelength and now a half a wavelength, now we have the ideal situation for DX. At a half wavelength, that same dipole is now sending out strong lobes to the side and almost nothing upward. So very good for distance, terrible for NVIS. Now you might have heard people say, how high should my antenna be? And people say, well, the higher the better. It just isn't true, because even if you're a DXer, 0.5 is ideal for a dipole. If you go up to 0.75, which is in the upper right-hand corner here, you can see you still have your lobes to the side, but now you've got a lot of wasted energy heading straight up. And this is just because of ground reflection. And so getting higher than a half wavelength is not a good idea for a doublet or a dipole antenna. And worse yet, if you get up to 1 wavelength high above the ground, the reflections cause you to have side lobes which are like this, where if you had fading, you might have a strong signal for a moment, and then the ionosphere would tend to move, and you would have a very weak signal as you're in this gap, and then you might have it strong up in the top here, depending on the angle of your path through the ionosphere. So a dipole 1 wavelength above ground will be very unstable, create a lot of fading. And back to the topic here, this is the best DX antenna, and this is the best NVIS antenna. And the only difference is how high above the ground, 1/4 wavelength versus a half wavelength. This is trying to show the same information about antenna height in a more precise manner. And you can see that this is the height of a transmitting antenna, and it is optimum for transmitting. That means gain. It's optimum just below 0.2 wavelengths. I was saying a 1/4 wavelength, that would be about here, down to about 1/8 of a wavelength. 0.125 would be about here. So anywhere between 1/8 and 1/4 is roughly in the sweet spot for a transmitting antenna for NVIS. You can see that the optimum spot for a receive antenna for NVIS is much lower. It's about 0.1 because that gives you the best directivity. It means you'll be looking at signals coming from nearly straight down while you'll be ignoring all the noise from off to the sides, like all those lightning and thunderstorms. General rule, to make things simple, is if you're anywhere between 1/8 of a wavelength to a 1/4 wavelength, you'll be in good position. You'll be in a good spot. And the nice thing about that is that an eighth wave at 80 meters is about the same as a 1/4 wave at 40 meters. And so you can use that same antenna, same height, about 25, 30 feet off the ground for 80 meters or 40 meters, and they'll both work very well. Okay. I'm going to pause again. We've talked about ionosphere. We've talked about the importance of antenna height. And now we're just going to look at a few antenna designs and then wrap it up. Any questions so far?
Yeah, Jeff, Bob, K6UDA.
Yeah, Bob.
Hey, on the dipole antennas, 1/4 wave to a half wave, 1/4 to half wave up. Say your standard G5RV antenna.
Right.
What would be a good 1/4 or half wave height? And is that at the ends or is that the feed point in the center?
Okay, good question. It depends on what you want to do. If you want to use that G5RV for DX and see how far you can talk, maximum distance, then you want it to be about a half wavelength up at whatever band you think is important. So if it's the 20-meter band that you want to focus on with that G5RV, then you want the antenna to be about 10 meters off the ground, and then the reflections will optimize that G5RV for DX. If you're looking for a 10-meter optimization, then a little, half that height. Again, in real life, we all know that whatever antenna you have is the antenna that works. I mean, depending on the conditions, it'll work. But at whatever band you're interested in, a half wave off the ground for a horizontal dipole will give you those nice wide side lobes for DX. But for NVIS, we're only focused now on the lower bands, 80, 40, and 60, because anything higher than that would penetrate through the ionosphere anyway. So we don't care about higher bands. But for the lower bands, 80, 40, and 60, the nice thing is, like I mentioned earlier, that 1/8 of a wave at 80 meters is a quarter wave at 40 meters. So really, you can just go with the simple rule of put your NVIS antenna about 25, 30 feet off the ground, and it'll be pretty much optimum for all three of those low bands. Does that sound right?
Yeah, no, that sounds good. So thank you.
Yeah. Okay. Any other questions about the antenna theory before we move on to some examples of antenna designs? Okay, moving on. Let's just look at a few examples of fixed base antennas. A lot of this came out of the military manuals from several years back. This is one that you may know as a fan dipole, and it's just 3 different dipoles, all with a common center point. It's simple. The advantage is you only need 1 feed line, and if you tweak it right, you'll get a reasonable SWR on all 3 of your bands. You put the lowest frequency at the highest point on this because, again, what we just talked about, the lowest frequency is the longest wavelength. It benefits from being higher above the ground. This is an antenna very similar to the one I have at my house here, which works really well. It's a full wave horizontal loop. And this one's square. Mine has actually 5 sides, which doesn't matter. Actually, this is a little better because it's closer to a circle. But the idea here is that the circumference of this loop is 1 wavelength at your lowest operating frequency. So I have an 80-meter loop. It's about 280 feet all the way around, and it works really, really well for 80 meters NVIS. It works pretty well at 40. It works really well at 62, but at 40, the problem is that this antenna starts to produce low angle radiation at the second harmonic of the base frequency. So it's really good for 80. It works really well for 60, but for 40, it's trying to do somewhere in between distance and NVIS. And this has about twice the gain of the optimum dipole. Here's a fancy one out of a military book. It's a log periodic, and it just has, I wouldn't suggest anybody build this, but it's kind of fun to look at. It has the advantage of very wide frequency response, very wide choice of operating bands. And so the military might use this back in the old days when this was their primary source of reliable communications, because they could operate anywhere from the very shorter bands up to the longer bands, depending on conditions. This one's called the Shirley Antenna, and you'll see places on the web where they say this is absolutely the best NVIS antenna there is. No, not really. It's kind of complicated. It's using, rather than dipoles, it's using folded dipole, and the reason for that was because they were using detonator cord for their transmission lines. They were using what they had in the field, and the impedance of the detonator cord was higher than normal, and so they used a folded dipole, which was about 300 ohms input impedance, rather than the 70 ohms of a regular dipole. And so really this complicated structure is all about matching the impedance of the cable that they used. As it is, just a regular dipole phased like this will give you the same performance, about double that of a single dipole, about 3 dB better. Here's the same idea, but instead of a half-wave dipole, they're using a full wave. And so they get about 3 dB greater than a half wave. They're using 2 of them phased, so that's about 6 dB total compared to a dipole. The problem with using full wave dipoles, they work fine. They're just really hard to match with the impedance, because just like operating an NFED half wave, this is 2 NFED half waves, and they're very high impedance, so matching can be a problem. So it's there kind of it was in the military manuals, but the fact is a simple dipole, or maybe a NFED ZEP, I'm not an NFED, but a double extended ZEP which is 5/8 going both ways, is the optimum antenna, and much simpler. If you use a ladder line, then you can use it on all the bands and with very little loss as well. So this is too complicated, but it's here as an example out of the history books. This is one that we see fairly often in the books, crossed doublets. And the screen reflector can actually add quite a bit of gain depending on what kind of soil you're over, how well it reflects. So it's just the idea that you would have two different bands crossed. So you might have a 40-meter doublet at right angles to an 80-meter doublet, and they're both fed from the same central point. And the fact that they're over a screen reflector increases the reflections quite considerably in the direction of straight up. Okay. Here is the same idea in an actual military kit. It's the AS-2259 Collins, this was very popular in the military. I don't know how popular it is these days. The central mast is actually a coaxial transmission line. It's a very high efficiency, so even if you have a high SWR coming down this center mast, you have low loss, and then you tune it with this antenna coupler here. So these elements coming off 90 degrees from each other don't have to be resonant, is the point. So the military can set this thing up very quickly. Doesn't have to be resonant. It'll work on a wide range of NVIS frequencies, and you can tune it here with low loss on the center mast. Here's one I've thought about for field day. Haven't done it, but if you only had room for one doublet and you did not have a tuner, then you could build it for multiple bands and just use jumpers to make it longer or shorter depending on the band that you wanted to work. Probably a better solution is to use ladder line and have a tuner down on the ground. Then you don't have to worry about the jumpers. Okay, and the last antennas that we'll look at are NVIS mobile antennas. Here's your standard 15-foot whip antenna on a Jeep, pulled back so that it's kind of horizontal. And you can see from the radiation pattern that it's not terrible, but it's not really good either, and it's very directional. But this would get some energy up toward the ionosphere. Here's one that's even better, where they fold it back over the front of the Jeep, and so it's more symmetrical, and the pattern is better for getting it up there. Still, as you can see, it's going to be more for distance at like the 45-degree angle rather than close to 90. But if you have a Jeep and a 15-foot whip, that's the way to do it. So here's something fairly modern. This is a Harris dual loop, and it works very well. It has very narrow bandwidth, but it has high efficiency. It's actually a magnetic loop antenna. The reason they use two loops is to increase the bandwidth, and so they can do some high-speed data. Don't see those on the market, but obviously they've got it on that Humvee. There's another one, another picture of the same thing. This is the Barrett half loop magnetic loop antenna. It works pretty well. It has the main advantage of being small. It's a little too small for great performance. You get quite a bit of loss in the capacitor that they're using to tune it here, and not a whole lot of length to radiate from. But it's very mobile, and this SUV type vehicle can travel around commuting reliably on the low frequency bands wherever it happens to be. I think they're about $6,000 if you want to buy one. Here they've taken two antennas on a military vehicle and connected them at the center to make a horizontal antenna. That's just another way to do it. I think that was a British military vehicle. Here's a Russian truck with half loop for NVIS, and they're using 2 of them together. They were serious about what they were trying to do there. And here's a ham, WB3AKD built this one. It looks to me like he was trying to go for 80 meters and driving around town talking 80 meters NVIS with his loop antenna. Impressive. Any questions so far? We're going to wrap it up in a moment.
Hey, this is Greg, KO6GH. How much power do you need to run this? Does QRP and NVIS go together?
NVIS has a path length which is pretty stable of just a couple hundred miles up to the top of the F layer and a couple hundred miles back down. So it's a 400 or 500 mile total path, and it's very stable. And for those reasons, you don't need a whole lot of power. So what do I mean? Well, the military man packs were about 30 watts, I believe. And most of what I've seen will work very reliably, very well on 100 watts, even a little bit less. You normally don't need anything more than 100 watts.
Yeah, I've got 6 in the car, so it's not gonna. Okay, thanks.
Yeah. Anything else? Any other questions on antennas? Okay.
Is there a
Yeah.
Oh, what's it called? The small loop antennas. Is there one that you'd recommend, like they were showing on the back of the Ndis?
Most of the loop antennas that I've seen commercially are about 1 meter diameter. And so they're really only useful for the higher HF bands, 20 meters and above. And if you do it right, they can be very efficient. You need to get one that has a vacuum variable capacitor to really have good efficiency. It depends on what you're trying to optimize. If it's for carrying to a mountaintop, you can trade off a little bit less efficiency, but they do work. In my backyard, I have a project I haven't touched for 2 years now, which is a 10-foot diameter, 33-foot circumference magnetic loop project. And it has a great big Russian vacuum variable capacitor. And I just need to finish building the controller to tune that, and I can put it into operation. And according to the design specs on that 10-foot diameter loop antenna that I have, the efficiency on 40 meters will be very close to that of a full-length dipole on 40 meters. The efficiency on 80 meters will be about 50% of a full-length 80-meter dipole. But the cool thing about this is they work extremely well only like 20 feet off the ground. They don't need to be a half wavelength off the ground or even a quarter wavelength off the ground to perform, because it's a magnetic loop, and the field doesn't depend on ground reflections. It just depends on it's controlled internally by the design of the loop. So when I get that 10-foot loop going, it should be very comparable to a full performance dipole, but without having to worry about height above ground.
Cool, thanks.
Any other questions on antennas or anything we've covered up to now? Okay. What I've done here is just listed some items that could be worth further discussion, but each one of these could be pretty much another session just like this one. So we won't get into them. I just wanted to list them for your information. Sources of noise. You can. Oh, that's the other thing about magnetic loops. They have a strong null. So you can, if you have a null source of noise in your local environment, maybe you're in a city, maybe your house is noisy, maybe your neighbor's house is noisy, you can turn a loop at right angles to it and pretty well null out the noise if it's close to you. But still, the high angle radiation will be unaffected. It's only the low angle radiation that is sensitive to the null. Distant lightning storms are worth talking about. Again, with the proper NVIS antenna, you can really minimize the energy from a lightning storm, which can be all worldwide. It can be thousands of miles away, but it's mostly propagating at low angles. And so if your antenna is optimized for high angles, you're not going to hear it. One of the characteristics of NVIS is that the signals just tend to pop out of the noise, as opposed to DX, where you have to pull them out of the noise. They're right there fading, and you're trying to pull that signal out of the noise. NVIS done right, it just pops out of the noise, generally speaking. EMI, RFI is kind of the same subject. Interference. The other thing about loops is they are very high Q, and so you need to tune them for, say, like a 30 kilohertz bandwidth, and anything outside that 30 kilohertz, you won't be hearing it anyway. So that's another advantage of the loop. Ground waves, we talked about that briefly. If you're on 80 meters, you'll be hearing noise from Sacramento, for example, that's being propagated, just from people's electronics, their air conditionings, power lines. It all gets propagated via ground wave, easily 40 miles. And if you have a vertical antenna, you hear all that noise. If you have a horizontal antenna, it's mostly insensitive to ground wave propagation. That's the part of the myth, the mythology of horizontal antennas being quieter. We could talk about solar flares and how they activate the D layer and tend to make everything go to ruin all the propagation. And I just want to emphasize that having an NVIS antenna down at the river and deep in a canyon is actually a good place to have it. There's a lot more we could talk about, but just to show you what topics are out there. The transmit and receive antennas are not reciprocal. You could optimize for a receive antenna separately from your transmit antenna and get a few dB gain. Grounds, reflective screens that we talked about can help. Just having a wire reflector underneath your dipole can help for NVIS. Fading characteristics, polarization. There's a whole study of how the ionosphere reverses the polarization, and so if you actually had a circular antenna, you could take advantage of that. That's the ordinary and extraordinary wave business, partly anyway. Polarization diversity, space diversity, multiple input, multiple output techniques, and digital radio optimized for NVIS. So these are all topics related to it, but we certainly couldn't get into them right now. Other techniques for regional communications, WinLink. I think we've all heard about WinLink. It's very powerful. You can use it on VHF, but you can also use it on HF. It's excellent for disaster relief and emergency, as well as for events like TEVIS and the Western Endurance Run. I was a fan of FSQ Call a few years back when it was a brand new thing. It was kind of like an electronic bulletin board system on 40 meters. Carl CKV and I used it for a couple months and had some fun. Now that's been replaced with JS8 Call, which is even more robust. And so, and this goes to Greg's question about power. If you're going digital, Greg, you can get away with just a few watts and still have very reliable communications digitally on NVIS. And then there's HF APRS. I mean, a lot of us have seen APRS on 2 meters. But the similar system exists on 30 meters, 10 megahertz, where rather than trying to get to something which is a repeater which is within less than 50 miles from you, you're actually intending to reach repeaters that are, repeaters is not the right word, but a station which is 500 to 2,000 miles away. And you can do remote positioning and other packet communications. Again, another example of digital reporting. So PACTOR, most of us are aware that PACTOR 4 is in the wings. It's ready to go, but the FCC hasn't updated their regulations to allow it. And a few more technologies, diversity for to handle fading. The military is all about high bandwidth, and so they do things about dynamic tuning and multiple antennas to improve the bandwidth for their battlefield operations. Then there's automatic link establishment, ALE, where you just you let your radio decide what band and what frequency to connect with, and then you can call people up by their ID number. That also uses selective calling. And we've already touched on amateur digital text, and there's digital audio on the HF bands as well. So kind of like what Greg did, I'm saying there's a lot of stuff out there if you want to play with it, explore, and push back the technological bleeding edges. Summary. I know this has been a lot, probably a lot of high-speed information. I hope it wasn't too overloading. Here's just a summary of the key points. NVIS does provide robust local and regional communications out to about 300 miles. There is no skip zone, regardless of terrain, independent of infrastructure. It's important to choose your frequencies for NVIS according to the ionosphere. Good rule of thumb, and this is back in the sunspot days. It was pretty typical that 75 meters after sundown and into the early morning, 40 meters after the sun has been up a while, 60 meters in between. With the way the sunspots are right now, 60 meters is the place to be. But we only have 5 channels there. But it kind of works all the time. And after you've chosen your frequency, you want to have, a proper antenna with high takeoff angle. It should be horizontally polarized between 1/8 and 1/4 wave above ground. So 30 feet is a good height for 80 through 40 meters, which is all we care about for NVIS. So apologize for the speed that we covered. We covered a lot of information. If anybody has any questions later on, feel free to contact me, either email or on the club repeater. And I thank you very much for your attention. Any other questions?
Yes, this is Earl. I have a quick question. ARRL puts out propagation information monthly on their website. Is there a site that a person can go to find the propagation, so to speak, as far as what is a good time of day for a particular frequency and the area of coverage?
Yeah, so Earl, the best source that I have found is that San Francisco Ionosonde data. And in addition to what I told Brian earlier, I remembered that another place to find that link is on the HF PAC, Hotel Foxtrot PAC website, HF PAC website. And they have ionosondes for various places in the world or in the country. But for us, the San Francisco Ionosonde would give you that information about current propagation conditions. And after a short while, you start to realize, well, if the sun's up, then it's probably time to switch to 40 meters. If 40 hasn't come alive yet, it's 60 meters. Otherwise, in the evenings and all through the night, 80 meters. Does that help you?
Yes, that's good information there. Thank you.
Any other questions?
Yeah, this is Carl in 60 kV.
Hi, Carl.
Yeah, I just want to point out that I check into the Cal OES net every Monday night for Placer County.
Oh, good. I didn't know if anybody had done that since Fred used to do it way back when.
No, I'm doing that now, and I also check into the Gordo net, the California Rescue Communications net.
Very good. Then you know what that Chinese broadcast sounds like.
Yeah, all too well. Every morning, every weekday. That's on weekday mornings.
Yeah. Thanks, Carl. And I do appreciate the couple months that you spent with me using the oh gosh, I've got a mental block. But the texting on computers.
Yeah. And good presentation. Thank you.
Thanks, Carol. Okay, any other questions, or we can turn it back over to Brian?